the generalization of this, you look at your system, okay, you find the phrases, the words, or whatever that are most commonly used, and you just list them and the frequency that they're used, okay, and then you make a tree, and you give the most used, the shortest code, etc. This is called Huffman coding, and it almost does as well, not almost, but it comes, it can do something similar to what Lempel-Ziv can do. This is something, I don't know how much I want to get into. This shows you how misogynistic computer scientists and engineers in general are, right? So, thanks. It's even open. Okay. So they had to use something as, for instance, a picture or a data set in order for people to try and compress it. Here's a Playboy Playmate of the Year. I'm not showing you the rest of it, okay? But that's what they chose to use for doing data compression, for seeing how good your data compression program is. What? Just the top, right? They didn't use the whole picture. Although it turns out the entire picture is well known to computer scientists. I found out. Anyway, this is an example of predictive coding. Another thing you do for coding is you just say, okay, I'm going to use the information I have before to predict what's next. If you do the simplest thing you can do, just to show what you can get from this, if you simply say the next pixel is the same as the previous pixel, instead of using 256 different numbers, okay, the number you have to add to get from what you have on one pixel to the next lies in a very small range. So even if you just say the previous pixel, the next pixel is the same as the previous pixel, you compress a lot. Okay, these are the guys that Lempel and Ziv, who happen to be at the Technion, which is where Dove is, came up with a scheme which is very heavily used nowadays. It goes like the following. It's called dictionary coding. What you do is you take your string that you want to compress, you put your cursor here, let's say. Your cursor is in this region because you've previously coded up to here. You have a dictionary, which is what you coded before, and a look-ahead buffer, which comes after. What you're going to do is you're going to write down a triple, which involves the position of the longest match, okay, before the cursor with what comes after, okay, how much you go back to where you found the position of the longest match, you tell how much to copy, the length of it to copy, and you put down what the next character is. And the best way of doing this is to just show you an example. So this is a string here. In this case, the buffer size is 4. That's the look-ahead region. The dictionary size is 6. That's behind the cursor. You start out, you give it a 0, a dash to say you are starting out, a 0 because there's nothing to copy at the beginning, and then the next letter, which is A. And you move your cursor over. Now you look ahead, you have this. You see an A there. You say go back 1, copy 1, and you put a C. 1, 1, C. Over here, okay, you look back at your dictionary. It's AAC. Here you have AACA. And here's where you start seeing the advantage of this. What you say is go back 3, copy 4. And that means cyclic. So it's AACA. Okay? And that's exactly what this is. So you put down 3, copy 4, and the next one is B. Okay? Now, why is this something that's interesting or powerful? Imagine it was from here on, it was AAC, AAC, AAC forever. Right? Well, not forever. Let's say for 1,000,000. Okay? What you would write down is go back 3, copy 3,000,000. The difference between a string that's 3,000,000 long and writing copy 3,000,000 is log of 3,000,000. The number of bits you need to write 3,000,000 is log of that. So you can save like log n over n by doing things like this. And then we go on. That's essentially what Lempel-Ziv coding is. Okay, it's used all over the place. I should have pointed this out to you. Actually, it's because I'm holding this thing. It's used in deflate and zip, all these things like that. What I forgot to show you before I lose this guy, okay, is the following. I want to show you how complicated it is to do this, okay? So what you do is, you go over here on your computer, you find the data file, you right-click it, and over here it says compress. Got it? Okay, so what I'm telling you is, if you want to know whether something is more ordered than something else, you know, and they're comparable sizes to start, or you can normalize by the length, you go over and you press that key and you compare the two files, okay? Okay, you should remember that. It's useful. Okay, here we go. Let me take this. Okay, this stuff is important. People have looked at it. It turns out that a lot of work was done on Lempel-Ziv by computer scientists, information theorists. You can find the redundancy, which is the difference between what Lempel-Ziv gives you and what the Shannon entropy is. Okay, if the Shannon entropy is 0, like for an ordered array, something, yeah, that you can write down. Something with no entropy, like a periodic sequence. Okay, the difference goes, you converge to it like log n over n. If the entropy is not 0, you converge much more slowly, but in a well-defined way, log n over n. It turns out the redundancy, the difference, is actually proportional to the entropy, which means you can solve this and find out at any n, if you know what your n is and you have a reasonable n, you can find out what the actual Shannon entropy is for such a system. Here's the way this works. If I take a random number, it doesn't compress, so as a function of the size of the system, the CID, the compression doesn't compress you, essentially. You just get something that's flat. If you have something that's periodic, it dies like log L over L. If you have something that's quasi-periodic, like a Fibonacci sequence, it goes like log squared. There are all sorts of weird things in this, okay, and that also show you lots of differences between, for instance, the Kolmogorov complexity and the Shannon entropy. One of the primary things is pi. Now, many of you may know this, okay? Pi is indistinguishable from either any compression algorithm that anybody has ever made or from the Shannon entropy, and this has been looked at, you know, a lot, from a random number. Pi is a random number. Its Kolmogorov complexity is 0, because you can write a short computer code, okay, that can give you pi to as many decimal places as you want. Essentially, this is a real problem. People have looked at it. it means in pi, if you wrote it out in binary, is all of Shakespeare, right? Okay, there are other things that are really interesting here. The Rudin-Shapiro sequence over here, which is going towards zero entropy, that is, for a very long string, its entropy is very low, okay, has no two-point correlation functions. So if you were to look, for instance, at Fourier transform, if you look at spectral function, what you would find is that it looks flat, just like a random sequence, but there's no entropy in it. And if I get to it, I'll show you how you can actually use that. How good does this do, you might ask? So here, for instance, is entropy of mixing. That's essentially the first curve I showed you for the conserved lattice gas. Here's what you find from Lempel's Eve. Here's what happens if you do an extrapolation, as I told you can do. This is just inverting the equation for redundancy that I showed you and solving for the Shannon entropy. You know, it's not exact, but it doesn't do too bad. Here's what any physicist would look at first, the two-dimensional Ising model, okay? If you use the same number A here as you did for the other, you're off. So you can't, A is not just a fixed number here for the extrapolation. But if you just take the, you take the compression and you fix the point at infinity, whose entropy you know very well, okay? This is what you get. And again, it's pretty good, and it gives you the critical point pretty well, but it's not exact, okay? It depends. So it depends what you mean. If you, for instance, if you take the logistic map, you can get the critical exponents and everything like that from doing this. Okay, you can compress it. Okay, and the compression depends where you are and whether it's chaotic and how chaotic and stuff like that. You can get the Lyapunov exponents and stuff. That's one of the first things we were thinking of doing, but then we found it had been done. Okay. How you make your string to compress, and the answer is, well, you can do a raster scan like that, you can do a range scan like that. The best one you can do is a Hilbert scan. A Hilbert scan is a self-similar scan, you know, where you take a system like that and you essentially decimate or inflate it, depending on how you want to look at it, until you cover the picture, okay, all the pixels in the picture. And this one has a sense of locality, that if you're local along the line, you're local in the space you're looking at, unlike a raster scan. Your camera tends to use a raster scan because there's a horizon, and things are correlated relative to the horizon. How much time have I used, actually? Oh, I can see back there. Great, okay. Now I'm going to do some physics, okay? Has everybody seen this movie? Has anybody seen this movie? This is a movie by G.I. Taylor showing you that low Reynolds number flow is reversible. I don't see lots of people. Has anybody else? No. So has everybody seen it? I'll show it. Anyway, okay, the only reason I say this is for sure, and I always say this, and it's always true, if you've never seen this movie before, it's the only thing you remember about the lecture, okay? So what this is two concentric cylinders with a viscous fluid between them. What G.I. Taylor, who's an amazing scientist, does is he puts red ink in there, and now he's twisting it around so he's shearing the fluid inside here, right? And low Reynolds number flow is reversible in a very specific sense, not like the laws of physics, where the laws of physics are the same going forward or backward in time. But here it essentially amounts to the displacement of fluid elements being slave to the stresses you apply, which here are all applied at the boundary. And he rotated it one way, and now he's rotating it back. And look at that. I've got to say, that's amazing, isn't it? Yeah. Okay. Now, this is a great demonstration. The question is, what happens if you put particles inside? So it turns out it's known for two particles at low Reynolds number. If you just take them and you shear them past one another, they do a dance around one another like that, and they even end up on the same streamlines, and nothing happens, and it's completely reversible. And you would think in low Reynolds number flow, you'd always get reversibility, and it would always work, and everything should be laminar and everything like that. But it turns out there's an experiment we did sometime in the 90s, okay, where we just looked at sedimenting particles at low Reynolds number, and if you just look at them, they look like they're just falling down. If you do time-lapse, you find it's chaotic, okay? And the same year as we did that, it turns out that this group showed that if you even take three particles, they're chaotic. Essentially what happens, if you have two particles, one of them falls in the flow field of the other, and they both fall faster than a single particle. If you put three of them, they do some sort of dance, and then two of them go off and leave one of them behind. And which one is left behind of this yellow, blue, and red ones depends exponentially on the positions, okay? So it's known that it's chaotic, okay? That doesn't mean it's not reversible, necessarily. Dave Pine, who's my colleague at NYU, did a beautiful experiment. He did G.I. Taylor's experiment with particles in it. So it's two concentric cylinders with a viscous fluid between them, and what he's just going to do is rotate back and forth and see whether the particles come back to the same place. He density match the particles so they wouldn't sediment, index match so you could see through it. And what they look like if you look from the side with the camera, and here you're only seeing 1% of the particles. The others are index matched with the fluid, so you see right through them. The particles don't appear. 1% of the tracers to watch what the flow looks like, and this is them going back and forth as you shear it one way and then the other, okay? And you can't tell from this whether they're reversible or not, okay? If you want to tell whether it's reversible, you want to strobe it, so you take a picture only at the same time each cycle, right? And what that looks like is this, and this is actually a movie. You can see they're moving a little bit. You can see stuff behind, which is junk falling behind the apparatus, okay? But they're not moving much, so it looks like it's reversible. So it looks like that answers the question, okay? This is at a strain of 1. The strain of 1 means you displace this surface relative to that surface by essentially the separation between them. That tells you that's like this amount, right? You're going like that, okay? Then they made the mistake of trying at a higher strain, like that, okay? And when they did that, it looks like this. Okay, clearly not reversible, right? This is strobed, okay? Okay. This, of course, this critical strain that you have to apply to get it not reversible depends on the volume fraction. Here's sort of a phase diagram for it. But what's really interesting is, until you get at a fixed volume fraction up to a certain strain, it's really reversible. And above that, it looks essentially chaotic or diffusive, okay? So this is really an interesting discovery, okay? So what's the explanation for it? So the explanation that they had was the following. They said, well, we know that 2 particles are reversible and 3 particles are chaotic. So it's probably, the more you strain it, the more you get 3 particle interactions, and if you only strain it a little bit, you get 2 particle interactions, etc. So I didn't like this, okay? I didn't like this explanation at all because I thought I knew something about random systems, having packed M&Ms. And one of the things I knew is if you have a random system that, you know, sometimes you have 2 particles together. It's less probable, but you certainly have 3 particles that are close together, or 4, as many as you want. So it can't be an explanation for something which has a transition, which has a real threshold. It can give you a crossover, but it can't give you a threshold. So I didn't understand what was going on, and I argued with them about it and stuff like that. And I told them this can't possibly be the right explanation. And the guys that did this, Pine and Jerry Golub, are very smart guys. So I said, well, either I'm wrong, or I'm just not explaining well enough. So I said, okay, I'll tell you what, I'll do a demonstration. I'll write a computer program, which for me is really unusual. I'll do a model and a simulation, and since I don't know how to do this, it's going to be the simplest simulation you can imagine, okay? So you put the particles in randomly, okay, in this simulation, and now you do an affine deformation to represent the strain you're putting on. Now there's real hydrodynamics involved with this because they set up flows and everything, and I don't know the hydrodynamics well enough to do that. So I said is I'll just do an affine deformation, take them straight across. If when I take them across they overlap, I'll say, well, they touched. I don't know what the hell's going to happen if they touch. All I know is they're going to move. So I'll say when I bring it back to the initial position, if they touched when I was during the cycle, I'll bring them back to the initial position, and I'll give them a little displacement, okay? And that will represent that something's going on. And mainly what this was to show is that even if I strain a little bit, everything's going to move, right? Okay. So I did the simulation, and it looks like this. So this again is strobe, so you're only seeing the particles after they come back. This is at a strain below critical, this is a strain above critical. That's what I discovered later, okay? These guys are active particles, they're moving. It looks like some of these never move, but they get infected by the other ones, as you see. And as this goes on, what you see is that the activity here is slowing down, okay? In fact, it stops. And this goes on forever, okay? Now, I did these one at a time when I was doing it, and since I'm an experimentalist, the first thing I did is I hit my computer on the side, and they didn't activate again, okay? So then I ran the simulation again that did the same thing, and as soon as I saw it the second time, I said, I understand what's going on. In fact, I understand their experiment. What happened is, these guys explored different configurations until they found a configuration when you shear them, they don't collide. So they've organized themselves by their collisions, right? And above some, you know, threshold, for some reason, they can no longer do that. They can no longer find a way to organize like that. And what we did is we then went back, Dave and I and his postdoc, Laurent Corte. Actually, I thought I had this in French. Anyway, to emphasize it was Corte. Anyway, and what you find is that the time it takes to organize below the threshold, it goes to 0. This is the activity, okay, or the number of collisions per cycle. It takes some time to do that, and the time it takes depends on how much strain you put on. And above the threshold, it also takes some time before it goes to steady state. And when you plot those two guys, you get this divergence at the critical point, which means this experiment shows you a second-order phase transition, not thermodynamic, but dynamic, okay? Okay. We then went, actually, that was the simulation. So then we went back and we did the experiment, and the experiment shows the same thing, to make a long story short. Okay? So this is a model we call random organization. And it looks a lot like what I was telling you before, and like some other models I'll show you, but it turns out I didn't know about those models. None of us knew about those models before we came up with this one, which is a continuum model rather than a lattice model. If you now do CID with this, and CID 10 years after the experiments and after that model came out, I think, you can see in that model there's a cusp, which are in CID versus, in this case, volume fraction rather than shear, since you can go either way. You again can watch the evolution and get the critical exponents for these critical slowing down. You see again that where the position of the see, you can compare, okay, what the states would be for all absorbing states, that is, for states where particles don't overlap when you shear them, okay, and that's the red guys here, and the dynamics gives you something less than that, which means you're more ordered. You can also ask whether the system's ergodic. And you might say, I might expect it to be ergodic. It's clearly not ergodic over here, because there are absorbing states that the system can never find by these dynamics, and you never sample those, okay? There are. I'm just telling you. I could prove that to you with a one-dimensional model, but in any event. But above, you see, you approach the states that are just the random states of the system, okay, the ones that you find by Monte Carlo. So eventually it goes ergodic, which is sort of what we expected, but we didn't know. Yes?
What exactly are you computing here? Are you coding the difference over time of the images?
Here I'm just coding the images. I'm just doing, in this case, a Hilbert scan. Yeah, I explained Hilbert scan. A Hilbert scan of the image. So it's just the image itself.
So that will first capture the pattern in the first image, which mostly then gets repeated if it's stable.
But we're not doing it with time. So there's no time in here except the evolution of those images. Right. It's interesting as well, since you know you can compress a movie, to do that. We haven't yet started on that. That's another dimension which will give more information about the system. There are other systems that do this. So I think what I tried to show you is you can actually learn something from this that you didn't know. You can ask questions about whether you see all the states, whether the systems are ergodic, things like that. You can discover new things that you didn't know before. Here's another model, which is very similar to actually the random organization model. If more than 2 particles on our site are active, you empty to neighboring sites, right, and the dynamics goes until you have not more than 1 particle per site. The dynamics is essentially shown here, which I think is the first time I showed you the real dynamics of these kind of systems. No, it looks very much like the random organization model, which is a continuum model. So you can do continuum as well. You have to worry about how you discretize space, right? But here's another one which has an absorbing state like that. Here's what it looks like. Again, the absorbing states are more ordered in some aspect that we don't yet know, relative to all the absorbing states you can find. And you expect this guy to be ergodic when it goes up. And when we did this, we didn't see that. Here are all the states. Here's what you find in the active states over here, and it doesn't look like it's approaching that in any sort of reasonable way. So that bothered me. So again, when you see something after you do the CAD, you go back and you look what's actually going on. Here is what's actually going on. It's actually forming a dynamic checkerboard, okay? Because it turns out what Stefano did when he did the simulation is he did parallel updates. And when you do parallel updates, when you empty a site, you empty a site. So you have an empty site there. And this thing evolves by itself to give you this alternating checkerboard pattern, which nobody had ever seen before. If you now go back, okay, and instead of doing parallel updates, you do random updates, it's supposed to be towards something that's ergodic. Okay, again, you can do the same things we were doing before and get the critical exponents for the critical slowing down. We're not just going to do absorbing state systems. That wouldn't be that interesting. We can do swimmers. One of the things we do is active matter. Here's this active matter system. This is a plastic particle made by Stefano Sakana, who's a professor of chemistry at NYU. He sticks a hematite particle over here. Hematite is a photocatalyst. When you shine blue light on it, it catalyzes the degradation of hydrogen peroxide to water and oxygen. You get an oxygen gradient in solution. The oxygen gradient causes what's called diffusiophoresis of the particles. Particles in a concentration gradient of a chemical will swim one way or another, depending on whether the surface rejects or likes that chemical. Okay? It'll swim toward a chemical it likes. So you have light-activated particles. You have active particles. Here they are. You turn on the light, they swim around. What's cool here, this was a study to show you something like what you'd imagine might happen for flocking or schools of fish or whatever, if you wanted to know whether it was physics or biology or chemistry that was causing that. Here, it's mathematics that's causing it. It's essentially, when you have the swimmers, when they come in, by the way, this shows you that when you turn off the light, there's no potential interaction between the particles, right? They just come apart. You turn on the light, they crystallize again. And the physics behind this, or the math behind it, is very simple. It's simply, when they touch one another, they slow down. So now, the flux that you've got from the velocity of those guys going out is less than the flux coming in. If you have the flux going out less than the flux going in, it builds up. It's unstable. It's like a negative diffusion constant. Okay, we want to look at this. Well, Melissa, as a graduate student in the group, is looking at these guys now. She hasn't finished the study, but you can see, as a function of time, the CID, the compression goes down when you turn the light off, and they disassemble, it goes back up. In the meantime, while we're waiting for those experiments, we looked at a model by Christina Marchetti, who's interested in these active Brownian particles in the course. So these are swimmers, okay? There's a model of swimmers, a simulation, okay? We're going to do the same thing with this. We're just going to compress the images as a function of time. We're not compressing the time, we're just compressing the images, and we're showing them as a function of time. So here is the initial configuration that we start with. It looks like that, okay? Then we let it go for, let's say, 10 to the 6 swimming steps, cycles, and we get these curves. Now, if we're over here, okay, what you find is the CID, the information density, is constant with time. The system is changing configuration all over the place, but the information doesn't change. You make a higher concentration like over here, and you watch it, and it goes along, and then it dives. And here what you find is after 10 to the 6 steps, you get a curve which is identical to the original one to here, and then it drops, and it follows that line. And if this were really entropy, okay, this discontinuity indicates a first-order phase transition. Yes?
What is volume?
This is the volume fraction, sorry, the density. So this is how much of space is filled with the spheres. Or in this case, this is 2D, I think. So it's the area fraction covered by the particles, okay? So here, just increasing the density. So here you can see that there's a first order phase transition. And now you go back and you look at what happened, and not surprisingly, over here, it looks like that, and over here, it looks like that. Okay, so you can see what happens, but it turns out seeing it was first order is something that people tried using different order parameters, trying to find the correct order parameter for this, and they couldn't really distinguish whether it's first or second order, but this shows it immediately. Now, what more can we do with this? And now we're looking for more things we can do. What about correlation lengths? Usually you get the correlation length by doing order parameter, correlation function, seeing how it falls down. Maybe you don't have to do it that way. So the idea we had was this, and this is just shown, for example, for an Ising model. Here's essentially a one-dimensional Ising model. Here's your spin configuration. There are correlations in there. What you do is you decimate it. You only take every other spin, okay, or every third spin or every fourth spin. Now the basic idea here is, if there's a correlation length in the problem, okay, what I'm going to do, by the way, is I'm just going to take this string and compress it, and see how much it compressed compared to the length of the original string. The same with this string, the same with that string, okay? That's what the CID is. It's a ratio, okay? So what you expect is that if your correlation length is bigger than the spacing between the spins you're looking at, you'll find correlations, and the information or entropy will be low. And once you decimate above a correlation length, the system will look random, so it will look just like a random system. And now you can do many things with this. One is you can simply say, as it approaches 1, okay, which means incompressible because it's random, you can pick an arbitrary number here and say, that's the correlation length. If you simply do that with an Ising model, a two-dimensional Ising model, this is what you get, and you get the right critical exponent for the correlation length, okay? Okay, you can do better than that. You can do some real stuff. That is, you can take... You can follow somebody that actually knows what he's doing, like Leo Kadanoff, okay? Leo Kadanoff says, well, like do real space renormalization. What you do is you divide the system into chunks and use a majority rule to say if there are more spins up here than spins down, I'm going to label this a spin up, right? And this one will be a spin down, etc., okay? And now I just keep on doing that as a function of the scale parameter, right? And now I can press that, and what I find is this set of curves, okay? This is for the conserved lattice gas